So far, we have created a program that captures the idea of a bank account and then specializes that concept into two bank account types, savings account and checking account. What we essentially have is a demonstration of encapsulation, which is captured here in our bank account class, and inheritance, where our savings account and our checking account extend the bank account class or inherit from the bank account class, and then offers variations on certain operations or data that it possesses. So we've modified the withdrawal behavior of both of these account types, basically ensuring that depending on what type of object you have, any attempts to withdraw will have very specific behavior. So what we've essentially done is created this design where we have a base class bank account that is inherited from by savings account and checking account. So what we can do from here is extend this design. What we'd like to do is introduce a new account type first and foremost. And what we're going to do is use that account type as a way to segue into another feature of object-oriented development, that of using interfaces. So we're going to create a new account type called a certificate of deposit, or a CD account. So we're going to add this third account, and as soon as we do this, we're gonna notice some changes that will need to be applied to our design. So first, let's understand what a CD, or certificate of deposit account, is, in our bank at least. The idea of a certificate of deposit is that you add a certain amount of money to your account, and it's held for a certain period of time. Generally speaking, you get a certain amount of interest. So maybe you buy a CD for 6 months or 1 year. And at the end of that year, you get your money back along with whatever interest accrued over that period of time. One interesting thing about a certificate of deposit, however, is that the amount that you use to create the CD can never change. Meaning, you cannot actually add or deposit additional funds to a CD account. What that means for us then is, let's say we were to create this class. So we're creating a new Kotlin class, and we'll call this CD account. If we said that this extended bank account, and at this point, I'm using my IDE shortcuts. On my machine, it's Alt and Enter. If you're on a Mac, I believe it's Options and Enter. You can select options to fix the errors that are showing up in your code that the static checker can find. So I'm just having the constructor invocation generated automatically. That's one of the options that's presented to me in my little list. So I've created a CD account, and I haven't done anything else for now. So this is all I've done. But based on the rules that I've specified for a CD account, namely that a certificate of deposit, whereas it can have an opening balance, it cannot have or accept deposits. As it's done here, I realized that the object doesn't properly capture the business rules that I need the application to follow. Because if I create a CD account, and I give it a starting balance, I am able to make a deposit. This all still works exactly the same as a regular bank account. And this is because one of the assumptions I made at the beginning, it turns out, is not actually facilitated by my current design. That is, I had essentially said that a bank account is able to offer these data as well as these operations. And it turns out that that is not the case. Because as far as my bank is concerned, a CD account is a bank account. It is, in fact, a bank account. So if a CD account is a bank account, but when I extend the bank account class, somehow I am able to perform operations that should not be facilitated by that account type, specifically deposit, then what that's telling me is that the ability to deposit is then not a feature of a bank account, but rather it is a feature of a specific type of account or accounts, but not of all bank accounts. That invariably means this ability to deposit needs to be removed from my base class, and instead it should only show up in some other area where being able to deposit makes sense for that type of account, but it should not necessarily be a feature of all accounts. So we're going to go ahead and make that modification. And it's going to require us to make quite a few changes to the code we've already written. And this is one of the reasons it's very important when you are building software to give a lot of thought and put a lot of time into your design first, so that you don't have to go back later and change code that you've already written, because that increases the likelihood of introducing bugs and other types of errors. But we're going to go ahead and make some changes, and we're going to see what our final design looks like. But essentially what we need to do here is take away this deposit feature from our bank account class, because we're essentially saying not all accounts are able to accept a deposit. So it's not a feature of a bank account. What we can say, however, is that certain accounts do in fact allow for withdrawals, or rather for deposits. So we need a way to represent the ability to withdraw, or the ability to deposit, in the accounts that support it, specifically savings account and checking account. Now, I could simply hop over to my checking account or hop over to my savings account classes and add that ability. I could just add the ability to deposit separately. But as you can imagine, I'll probably end up repeating myself again, and that's one of the things that we want to not do when we're writing software. We don't want to repeat code. So the question is, what is the proper way to design my application that captures this ability to do a deposit that can be reflected in any class that is supposed to support that feature? Well, what I'm going to do here is I'm going to introduce a new concept as sort of a way to formalize this specific behavior that I want to capture and then implement in different classes. I'm going to capture this behavior or represent this behavior in something called an interface. So that's going to be my first step. I'm going to create a new interface. So I'm right clicking on Kotlin, I'm selecting new, and I'm selecting Kotlin class or file. You're not seeing my menu. That's because of how my software is capturing. But if I were to say switch to screen, then you could actually see the menu options that I'm selecting. So it's here, new Kotlin class or file. So that's kind of what I'm doing when I'm narrating the menus that I'm clicking on, but that you're not necessarily seeing. So I'm going to select new file, and I'm going to give it the name depositable. And I'm going to select interface. So this is a new interface that I'm creating. So what is an interface? Well, an interface essentially is a contract. An interface is this idea that you are saying that any class that implements a specific interface is guaranteeing that it will either provide the functionality specified in that interface, or the class itself will be abstract, which means you cannot have any instances of that class. There will be no objects of that class type. So the interface is a guarantee. It is a contract. If a class implements an interface and you have an instance of that class, then you can absolutely invoke any functionality defined in that interface. What behavior you will get as a result depends on the implementation, but you at least know the functionality will be there. So in Kotlin, interfaces can do a little more than interfaces in Java, but the basics are still here. Specifically, you are able to define a function, in our case, the deposit function, is essentially listed as a depositable function. The implication is any class that implements the depositable interface must provide a function called deposit, which means I can now expect that function to be there and I can invoke it and get whatever behavior the implementation has. So I've added this interface called depositable, and I would like to represent that on my UML diagram. This is my class diagram. So I'll place this here. We may have to make some changes or move things around in a little while, but this is my depositable interface. And the naming convention is usually something-able, meaning that whatever class has implemented this interface, its instance, its objects will be able to do the thing. So depositable, they will be able to perform a deposit. Again, that's just a naming convention. It is not a rule or a law. So this is the interface that I've defined, and it has the deposit function. Now I need to essentially implement this interface, and I have a couple of options here. Perhaps the most straightforward option is simply to select the accounts that are able to perform a deposit and specify that those accounts implement the interface. So for instance, I can come here and I can say savings account. In addition to inheriting from bank account, I can also say it is implementing depositable, and I simply list it as I would the class that it extends, just placing it after a comma. Classes can implement multiple interfaces, and if I wanted to implement additional interfaces, I will just add more comma-separated interface names. Moment I tell Kotlin that this class is implementing the depositable interface, I get this red underline, basically letting me know that my class, as it stands, is incomplete. So I'm being told there's a problem here. I can address that again by just using the IDE's shortcuts, if you will. So I can just hit Alt-Enter and I'll get a list of help suggestions. So implement members is basically saying, add the functionality that is missing, or I can have the class be made abstract. One of those two things has to be the case if I'm implementing a specific interface. Either I'm going to have all of the features defined in that interface, or the interface will be made abstract, meaning you cannot create an instance and you can only have classes that extend your class or anonymous classes that subsequently implement the functionality. Only those things could exist. Only those classes could have objects. So I actually want to implement the members, So if I select that option, I'm asked to select the function that I want. In this case, it's deposit. That's the only function I have defined. And once I do that, I have the code generated for me, and I can now add the deposit feature. Similarly, I would then go to checking account and I would do the same thing. I would say that this extends or this implements the depositable interface, and then I would add the function as well. Now, the problem I have is kind of the problem I had in the beginning, which is I'm repeating myself, right? So with that design, what I essentially would be doing is saying that that particular class, that particular interface is being implemented. And I'm trying to find my proper relationship arrow here. So what I would basically be saying is that savings account and checking account would have both implemented the depositable interface. And I would have essentially gone ahead and added the required functions in each class independently. But that's actually not the best way, in my opinion, because again, I'm repeating myself. I'm adding this deposit functionality multiple times. And that might be necessary, but in some instances it may not be. I think a more useful way of doing this is recognizing that while this interface is essentially specifying that a feature is needed if it's implemented, and I see that these two classes have implemented it and because they need the feature, I think there's another way where I could simply abstract this idea of a certain type of account that needs to have a deposit feature, and then basically have that class exist as its own class type, and then have it serve as the base class for my savings account and my checking account. Basically, what I want to have is a design that looks more like this. So I will create a new class type. Let's call this class depositable bank account. And a couple of things are going to happen here. Basically, a depositable bank account is going to be the class that both savings account and checking account will inherit from. In turn, depositable bank account will extend bank account, so it is itself a bank account, and simultaneously a depositable bank account will implement the depositable interface. With this design, what we essentially are saying is that a savings account will be a depositable bank account, which will have a deposit function because the depositable bank account class would have implemented the depositable interface. So there is a guarantee, if not a requirement, that this function either exists inside the depositable bank account class, or depositable bank account would be made abstract, which would then force savings account and checking account to implement the function themselves, which would be similar to them simply directly implementing the interface. So since I'm taking this roundabout way, then it would only make sense that I actually have some ability to perform a deposit in this class. At the same time, I will now have a CD account, which is kind of what sent me on this journey in the first place. My CD account will still be a bank account, and it will be a bank account, but it will not have the ability to take a deposit, which is exactly what we wanted. We wanted to make sure that a particular bank account, any bank account, could be used whenever I need a bank account, but only certain bank accounts could accept a deposit. Specifically, bank accounts that extend the depositable bank account class, which by doing so would have indirectly implemented the depositable interface. So let's go ahead and actually change up our design to reflect, or change up our code to reflect this new design. So again, a few changes are going to be made here because we did not start with the design in full, and instead what we did was we built up over time. So whenever we make a change to our design, it may necessitate us coming back to our code and modifying it. So what we're going to do first is, well, we notice that we're seeing errors here because right now this bank account is trying to make a deposit, and that's not a feature anymore. But we'll come back and fix all of this in one go. So let's first create some of the missing features. Specifically, what we want to do here is we want to create a new Kotlin class that we will call depositable bank account. This depositable bank account will essentially extend bank account, and we want it to have constructor invocation, and additionally it will implement the depositable interface. Because it implements the depositable interface, it needs a deposit function. So I'm going to implement the deposit function. Now, I'm not going to write the functionality here just yet because it's actually going to require that I come back and make some additional changes to my code. I'll talk about that at the end. But I'll leave this for now so that at least as far as the rest of my code is concerned, we should be able to compile, write code and compile it. So yes, I will have to come back and do this. Now, what I'm going to do is, per my design, I'm going to change the parent class for my savings account and my checking account. And instead of having them, as the code currently shows, instead of having them directly inherit from bank account, I am instead going to have them reflect this new design and have them inherit from depositable bank account. So savings account, I had written this prior, so I'll delete that. So savings account is no longer going to implement depositable directly. And it will not extend bank account directly. Instead, it will extend depositable bank account. Now it's telling me that I need to make depositable open. But I'll go one further. Instead of making depositable open, a depositable bank account rather, I will go ahead and make it abstract. The idea is, again, the whole purpose of depositable bank account is to serve as a base class, or in some cases to serve as a type. But I don't want you to be able to create an instance of a depositable bank account. You have to create either a savings account, a checking account, or a CD account. Those are the accounts I want you to be able to create. So by making a depositable bank account abstract, it is now automatically or implicitly open, and as such, savings account can now inherit from depositable bank account. Similarly, I'll go to my checking account, and instead of it implementing or extending bank account, it will extend depositable bank account. And at this point, we essentially have this design where depositable bank account implements the depositable interface, and then both our savings and checking account extend depositable bank account, which in turn extends bank account. So all of the account types here are in fact bank accounts by direct or indirect inheritance, but only some accounts are depositable bank accounts. So we're going to see how that works when we look at our code and go to our main class. So let's see what the impact or the result is of all of this. So right now, what we're doing is our bank account value, our bank account property, is essentially taking on the type of whatever object we assign to it. So in this case, it was a CD account, just arbitrarily. So bank account was of type CD. That is why I do not have the ability to make a deposit, because CDs do not have a deposit feature. Bank accounts by themselves don't have a deposit feature. But if this was a checking account, then we'd be all good, because a checking account, being a depositable bank account, does in fact have a deposit function. So this feature works. Now, I don't have the implementation for deposits, so I won't bother running the code because you won't see the result. Recall that the deposit feature is not yet implemented. So, but we have the ability to at least invoke the function. So we can do that with a checking account. Similarly, we can obviously do it with a savings account. Now, what's very interesting here is that with our design, we've actually introduced quite a few different types into our program. We, of course, have our savings account, our checking account, and our CD account. But we also have a bank account, and that is a type. We have a depositable bank account, that is a type. And in addition to serving as a contract, and again, serving as that guarantee, an interface also serves as a type. So you can have an object that is of type depositable. And this is actually very important. In my design as it is, it's relatively simple. And as such, as far as types are concerned, some of this is superfluous, meaning you in fact will have any class, any object that is of type depositable bank account is also of type depositable. And that makes sense. However, it is possible that I could have a more complex design where this interface is used or implemented by some other class that is not a depositable bank account. If it makes more sense, imagine I had an interface here, not for the ability to take a deposit, but maybe for the ability to generate interest. So we had an interestable interface. And perhaps my checking account was implemented that interface, maybe even my savings account. Well, certainly my savings account, I should say, maybe my checking account also does. But you may also have a credit card or a loan or something else, which may not qualify as a depositable bank account, but it's something else. And that other class also implements the interestable interface. In that scenario, you would not necessarily have the redundancy of types, of two types that describe all objects below it. And you may in fact have independent objects that do not share the same identity. So there are different types. Their inheritance tree is very different, but they still implement the same interface. That is very useful because it means that in certain instances where you want to accept an object or you expect a certain type of object, for example, if we had a function, since we're working with the deposit, we'll stick with that feature. So I want to let's see, batch process deposits. So I have a function that I want to batch process deposits, or something else, validate deposits. Since batch processing would suggest taking in a collection, and we don't want to start looking at collections here. So I just want to, there's just some function that allows you to validate deposits, assuming that we kept a list of all the deposits that were made. And the idea here is I want this function to accept an account. Well, what accounts would I be able to do? All right, so it's a bank account. But what's the type here? So if I just said bank account, and I wanted to validate deposits, this wouldn't work, because it turns out in this scenario, bank account would not have a deposit feature. The things that are related to bank accounts don't apply here, because not all bank accounts have deposits. So I would have to do a lot of checks or casting or different things and hope that I don't have a class cast exception or something and crash my program. So I could be specific, right? I could say, all right, savings account. So I know a savings account can take a deposit. So if I did bank account dot, see, there's the deposit function. So I can invoke that functionality. But my checking account can also take a deposit. So how would that work? Well, right now it wouldn't. I'd have to create a separate function So I would have to overload the function. And this might be useful if it was such that these two functions behaved very differently. And even though they shared the same name and a similar signature, they actually were very different in what they did. But assuming they were doing more or less the same thing, then having to have two functions for each type, and if I had more account types that accepted deposits, I'd have to have a new function for each one. That's the definition of repeating yourself. I'm absolutely breaking the do not repeat yourself principle. But this is where the types come in, and this is where having an interface that defines a particular functionality or a particular behavior that I'm interested in can be useful. Because here, where I need to pass in an account type that is able to accept deposits, it is sufficient for me to simply say that you should pass in, whenever you call validate deposits, you should pass in a bank account that is of type depositable, the interface. In this scenario now, it does not matter whether you pass in a savings account, a checking account, or what have you. It will always have the deposit function. And because I've specified this type here, I am in no way concerned that you can call this function with some object like a CD account that does not implement depositable. Kotlin will not allow you to call this function. So I could not say validate. Well, let's remove the, so we don't have this red. I could not call validate deposits with a CD account. It wouldn't work. I could only call it with a checking account or with a savings account, because those are the only accounts right now that are depositable. Now, again, I'm working with types directly here, because whenever I create an account of a particular type and I assign it, Kotlin immediately takes the type and assigns it here. But there are times, for example, in the example I just gave you, where the property type may be defined prior to the assignment of the object. And in that scenario, we actually have something very interesting that happens when we write our OOP programs. For example, I could say that this bank account class is of type, this bank account variable rather, is of type bank account. And at this point, I am able to put a checking account object inside that property, or to the more technical term is that this property will point to this object in memory. The reason this is valid, of course, is because it turns out a checking account is a bank account. It is of this type, and we can see that in our design diagram. A checking account is a depositable bank account, and a depositable bank account is a bank account. As such, a property of type bank account can hold an object or point to an object that is of type checking account or is of type savings account. So this is not a problem. It would be a problem if we said that this was, say, depositable, and then we attempted to assign a CD account. Because a CD account is not a depositable. The only depositable accounts that we are able to create are savings account and checking account. But a CD account is a bank account. So if we were to use bank accounts as our type, we have no problem. So if we had the general bank account and we wanted to perform an operation such as withdraw, the question is, at the time this code executes, which withdraw function is invoked? Well, we actually know that it is the withdraw function defined for CD account because the object inside this variable, as we've written our code here, is in fact CD, the CD account type. So it's known basically because of the simplicity of our code. But if we had a function that accepted a bank account and then performed the withdrawal there, the question becomes, which withdraw function would be invoked when this perform withdrawal function is called? And the short answer is, at the time this program is compiled, we don't know. Anything could call this function. I could call the function from here, or I could have an if statement where under certain conditions I call it with a certain object type, and under other conditions I call it with a different bank account type. So sometimes it might be called with a CD account, sometimes with a savings account, sometimes with a checking account. And what's interesting is that this still works because of something called polymorphism. The idea is that the type of object, in this case, as savings, checking, or CD, any of those objects can be passed into this perform withdrawal function because all of those objects are in fact bank account types. However, they all have different withdraw functions. The thing about it is, Kotlin doesn't care that they all have different withdraw functions. Kotlin doesn't care that a savings account limits the withdrawal to making sure that you don't have a zero balance, or that a checking account allows you to withdraw up to $50 beyond your balance, or in this case a CD account has no controls whatsoever. So clearly that's incomplete. We need to come back in here and modify some stuff, add a withdraw function to create some controls. For example, maybe in this scenario you are only able to withdraw the full amount, so we could easily implement that. Since it's a CD, you can only close the CD, so you can only take out all your money. You can't do anything else. So we could implement that feature. So we have all of these different withdrawals, but Kotlin doesn't know or care which one is going to be invoked at this point when this line of code is executed. Instead, what it will do is it will figure it out at runtime. Now, under the hood, there are all of these technical terms, things like late binding and all of that it relies on. But the implication is this function is going to behave differently. This function call is going to behave differently depending on the object that is passed in, whether it's a savings account, a checking account, or a CD account. And that is fundamentally what polymorphism is. It allows me to write simple, straightforward code like this, but have it behave differently depending on the context. And the context in this case is which object is going to be passed in, because multiple objects fit the bill if you just want me to pass in a bank account. So that's what polymorphism is. It's this idea of invoking different functions depending on the type of object I'm operating on, or different function implementations, where they all share the same name, depending on the type of the object on which I'm invoking it. So Kotlin doesn't check what object it's going to perform the withdraw on until it gets to the point where it's executing it. Only then does it actually look to see which object is this bank account property actually pointing to. Is it a CD? Is it a savings account? Or is it a checking account? And then it finds the correct withdraw function definition and executes it. So polymorphism, when it's happening, it's oftentimes invisible. We're not using any specific keywords. We're not doing anything fancy here. Polymorphism, rather, it comes out of our design. It comes out of the fact that we've created this specific design for our application, where the notion of a withdrawal is redefined in each of our bank account class types. And then Kotlin only looks for the type that it needs to invoke when we try to invoke the function, because at the time, based on the code we've written, all it knows is that the thing inside of the variable, the thing that the property is pointing to, is a bank account. And then it figures out which one it is later and which specific withdraw function it needs to invoke. So the last thing I want to talk about here is just something that we've left incomplete, and that is because it requires me to sort of revisit something. And that is in my deposit of a bank account. Whereas before I had my deposit function complete, here I've left it incomplete. And that is because fixing this or completing this function is not going to be as straightforward as I would like, as it was in the beginning. And that is because of the access modifiers that I have set up. So recall that the ability to maintain a balance and everything else is defined in the bank account class. That's where my balance is actually stored. And the balance property is private, which means it can only be accessed from within this class. So when I wanted to do a withdrawal, I was calling on the withdraw function in this class. When I wanted to do a deposit, I was initially calling on the deposit function in this class. But I've since moved the deposit function because we've determined not every bank account has a deposit feature. So it's now been moved to this new class, deposit of a bank account. But if I attempted to perform a deposit operation here, I would run into a problem. Because remember that balance is defined as private in the base class of deposit of a bank account. Because it's private there, it means I cannot access it here. My deposit of a bank account class cannot access the balance property, so I cannot change it in any way. Now, there are ways to address this, and they take different forms. But fundamentally, it means I may not be able to use private as the visibility modifier for balance anymore, not if I want to actually allow this to be changed. So the question becomes, well, what do I change it to? I can't make it public. Public literally will break all the things we were talking about before. It breaks encapsulation because it means any class could then reach in and change the balance of an object without any of the controls provided by the withdraw function or my yet to be implemented deposit function. So public use is not going to work. It is possible I could use protected under certain circumstances. Protected basically means that a variable or a value is accessible. And I'm going to just get rid of this for a second. This is causing naming issues because of the fact that a public getter is generated for this value automatically for the Java virtual machine, and it's causing a name conflict. So that's just a technical detail. You don't have to worry too much about it right now. But basically, having this be public or protected and simultaneously having a function that is called get with the name of the property, that's going to cause a name conflict. So as I was saying, I could make this protected, but we run into the problem where not only can deposit of a bank account access it, but then we could also access it from savings account and checking account. Now that may be what you want, but it's something you would have to decide on. Basically, when something is protected, everything along the inheritance hierarchy, everything down, every descendant is able to access it. So if we define it here and say it's protected, CD account can access it, depositable bank account can access it, savings account and checking account can access it. Now, what's important there is that main cannot access it. So that may be sufficient. That may, in other words, you may decide that if you were building this application and you wanted to you were the one charged with creating all of the classes for the bank accounts, or you and your team, you may decide that every bank account object is able, every bank account class rather, and therefore the objects that come from them, is able to manipulate the balance property directly. You may decide that. And if that's the case, then it does mean that using the protected property would work. But just appreciate that by doing that, you've relinquished control. And the onus is then on you to ensure that no other class misuses its access. Because that's one of the goals of encapsulation, making things simple, not just for the user, but also ensuring that they don't inadvertently break things by misusing a property or misusing a helper function. So you could do protected. The other mechanism is to create it as an internal property, but this part is tricky. And this is because of how Kotlin defines internal. Basically, in Kotlin, internal means you are able to access the property, an external entity is able to access the property if it is part of the same module of the program. And a module can be thought of as all the files that get compiled together. So it means that in that scenario, main here can access balance because it's all in the same module. They're all being compiled together. So you may ask, and then it seems like internal is not the best bet. And I'll say yes and no. Internal would not be the best bet in this situation where all of my classes are being built and compiled together. However, if it were the case that I was creating, say, a module that managed only the bank accounts and not any of the classes that use those bank accounts, then using internal here could be useful. In other words, what it would allow is for me to build a separate module. Maybe just I could have a module that only has bank account and depositable bank account together, nothing else. I could then make the balance property internal, compile these two together as a module, allowing depositable bank accounts to access the balance property, and then add that new module that I just made, introduce it to the rest of my classes, to the rest of my code. So now CD account and checking account and all of those other things, they would now use the classes defined in the module, but they themselves would not have access to the balance property. So it basically means it would be protected from even the other bank accounts because those bank accounts would not be in the same module. They would not have been compiled together. So that's perhaps that's the option that gives you the most control and the most protection, but of course it takes the most steps. You basically have to create this as a two-step process. Create the core base class module first, where properties are able to access the balance, entities are able to access the balance property, or you make it protected understanding that all of the classes that extend bank account, which for us are all the bank account types, clearly, would have access. And then you just need to be that much more careful that you don't inadvertently manipulate the balance property when you didn't mean to. In Java, another way to do this would have been to just use the package private option and just put the depositable bank account and the bank account class in its own package. And that would have actually solved it for us. All right. So that is the basics. Again, we have that little consideration at the end about how we manage the balance, and we have options available. But by and large, this is some of the major considerations that you will have when you're building object-oriented programs. When we get into Android, you will find that these concepts show up a lot. Inheritance will show up a lot. Interfaces will show up a lot. Understanding the concept of polymorphism and simply designing your classes such that you exploit encapsulation is going to be important. As we build more apps and move into Android, you'll become more familiar and more comfortable with the language and be able to use it to build very interesting mobile apps.